My name is Daniel Little, and the title of this talk is Human Scheduling of Perceptual Decisions. We often have to make decisions by considering multiple sources of evidence. Likewise, we often have to complete tasks comprised of multiple component subtasks. In many cases, the steps are contingent, requiring one to be completed before the next can begin. But equally often, we have a choice in the order in which we complete each step. Scheduling theory is concerned with the development of policies which determine the optimal allocation of resources over time to a set of tasks. This has been studied extensively in operation management and computer science, where optimal policies have been determined for many cases. There's almost no research on how cognitive and perceptual mechanisms perform with respect to these optimal policies, even though it is clear that scheduling is important to a number of tasks of real-world and theoretical interests. From baking a cake, to visual search, to processing multiple dimensions in categorization, many interesting theoretical concepts like capacity or attention shift costs are important for scheduling, but there has not been a comprehensive study of whether people are sensitive to the efficiency of different completion orders. We ask, when given a set of perceptual decision-making tasks to complete, do people complete these tasks in an optimal order? And if not, what order do they complete the tasks in? In our experiments, on each trial, we present participants with a set of random dot motion tasks. Participants have to complete each of the random dot judgments one at a time by clicking on each patch to start the motion and then responding left or right. Random dot judgments are useful because difficulty and the time needed to complete a judgment can be controlled by varying the coherence of the dot motion. We used 4 different levels of difficulty: easy, medium, hard, and very hard. The optimal completion order depends on 3 factors: the goal, how long each task takes, and the reward for completing each task. For instance, when your goal is to complete all of the tasks and they are of equal difficulty and value, then the schedule is unconstrained, as shown in row 1. When the goal is to minimize the number of tasks completed after a deadline, then the optimal order is to complete the task from shortest to longest. If tasks vary in difficulty and value, then one can construct an index of reward over time and complete the tasks in that order. The intuition is that tasks should be completed from shortest to longest unless a task is more valuable. If a task takes twice as long, then it should be twice as rewarding before you prioritize it over a shorter task. We conducted 2 experiments comparing long versus short deadline, whether the difficulty location was fixed or random across trials, and whether there was a time penalty for incorrect responses or not. The results of Experiment 1 and Experiment 2 were essentially the same, so I'll just report Experiment 2. Participants were told that their goal was to complete as many tasks as possible before the deadline. We recorded selection order, accuracy, and response time. If an error was made on the motion direction judgment, the direction was resampled at the same coherence. Each random dot motion had to be completed correctly before the next one could be selected. This table shows the average number of correctly completed tasks in each condition. The main result was that fewer tasks were completed under a deadline. Response time and error rate increased with increasing difficulty as expected. Accuracy was higher in the fixed condition than in the random condition. Response time increased more with increasing difficulty in the fixed condition. To confirm that coherence offered a good proxy for difficulty, and hence that an optimal order of easiest to hardest was maintained, we calculated the reward rate for each patch by finding the proportion of correct trials divided by the average duration between decisions. This figure shows that in all of our conditions, the reward rate increased from the very hard to the easiest condition. These heat maps show the proportion of selections of each difficulty made in each order. If every decision were optimal, there would be 1s along the diagonal and 0s on the off diagonal. It appears that the selection was more optimal when difficulty was in a fixed location and when there was a deadline. We wanted an index of how distant the response order was from the optimal order. This is given by the edit distance, or the number of discordant pairs, which ranges from 0 to 6, with 0 being optimal when there are only 4 options. Because a participant might not finish, there may be missing values, so we found the orders which partially matched the selected order and computed the minimum edit distance between the partial matches and the optimal order. Responses were more optimal, meaning more of this distribution was near 0, when the location was fixed and when there was a deadline. In order to characterize performance, we examined 3 sampling distributions for comparison to our data. Then we computed the KS test statistic between the data and the random order distribution and the first 2 optimal distribution. So the 3 sampling distributions we considered were the distribution if the first choice was just random from the set of 4. The second sampling distribution was if the first choice was optimal but the second choice was random. And finally, if the first and second choices were optimal but the third choice was random. Smaller KS statistics indicate a closer match between the distributions. So we took the ratio of the KS statistics by comparing our data first to the totally random distribution and dividing that by the KS statistic against our data for the first 2 optimal distribution. Here, values less than 1 indicate that the data are more consistent with random than optimal responding. Values greater than 1 indicate that the data are more consistent with optimal rather than random responding. The figure on the right indicates that there was more optimal responses in the fixed location condition late in the deadline condition compared to anywhere else. In conclusion, people schedule tasks more optimally when the location is fixed than when it's random. This is likely because there are additional search costs when location is random. Scheduling is more optimal when there is a deadline. Okay, but why? The next step is to explore individual speed accuracy trade-off thresholds as a driver of scheduling choices. Future analysis will consider whether different orders have equivalent time costs. For instance, some swaps might be more costly to response time than others. In future experiments, we'll examine other tasks other than random dot motion, a greater number of subtasks, so increasing the number of subtasks beyond 4, and dynamic displays where the difficulty of each subtask can be extracted from a glance rather than from a label. I'd like to thank my collaborators Eidels and Deborah, and thank you.